Hi everyone, my name is Dennis Dykeman. Presenting with me is Tanner Ham, Mark Young, Anselmo Gill, and Brian Rodriguez. To our right, you see our complete design model. It is an omnidirectional solar capture project. When designing this project, this model, we had to come up with some research questions, a hypothesis, and a purpose. The two research questions that we developed were how will the different environments influence the design approach, and how will the requirements be incorporated into the design. So for the first research question, we thought that the different environments of extraterrestrial planetary environments would have a different impact on our design approach. It would not be the same environment as Earth, and therefore it would need to be thought of differently. The requirements would also need to be incorporated into the design from NASA in the abstract that we were given, and then developed by our team. The hypothesis is that the created system shall be able to capture and transmit solar energy while meeting the requirements set by the team. So for this hypothesis, we thought that it would be important for the system to be able to complete the goal while also meeting the requirements that we came up with, again, by the NASA abstract that we received. The purpose of the study, purpose? The purpose of the study would be to design a system that can efficiently collect and harness solar energy while also meeting the requirements that I previously mentioned. The limitations or constraints would also have an impact on our design approach. The first constraint is a lack of time. We did not have a lot of time to complete this project, but I do think that in the time that we were given, we have completed a significant amount of work. The second constraint is a lack of physical resources. We have met only online, not in person, so this whole experience has been quite challenging because we have no physical resources. We have no computer lab, no classroom. It is solely online communication. The third constraint is the team's lack of prior experience with design software, engineering thinking, mechanical systems, and simulation software. Similar to physical resources, we have no experience. We have no know-how. I just met my whole team less than a semester ago, and we have come together with one common goal to complete this design. But I do think, again, that we have done significant work in that time. I will pass it off to Tanner now, who will present the next slide.
So this project allows for us and future studies to have a better understanding on how to collect and harness the use of solar power on extraterrestrial planets. Dang it. So the main purpose of that was actually the right slide. Dang it. The main purpose of this solar energy concentrator is to concentrate the light reflected off the parabolic lens towards the Fresnel lens that is located at a focal point. This parabolic reflector helps redirect the incoming light rays towards a central focal point where we have the Fresnel lens positioned. And I'm going to hand it off to Mark Young.
All right, guys, thank you very much. So from here on, we're going to be talking about the Fresnel lens. The purpose of the Fresnel lens was so it could direct all incoming light from a light source that may be at different angles, the individual rays from each other, so they're coming out parallelized to one another from the central rays in the center of the lens, almost like a laser beam. So the purpose of this was that we could take light from anywhere around the capture device, have it directed to a central point, and from there on it would be concentrated and sent down fiber optic cables to the solar panels to be turned into electricity. The Fresnel lens was critical in our application here, so we could collect as much light possible, whether it be from the bottom being reflected back up through the parabolic reflector that Tanner designed, or whether it be from above at an odd angle all the way to just above the lunar horizon. Next. Once we had our basic design for the Fresnel lens set up, we decided to use Unreal Engine 4 for its real-time ray tracing technology so that we could actively see where the light was being cast and how it was being reflected and refracted by the lens. That way we could see at any angle where it was coming from, being redirected to instantaneously without having to stop, pause, rearrange, and start over again. To set up for this, we had to have a bunch of parameters to meet real world window glass, which was used as our base material. For this, we need to have the reflection, refraction, Fresnel, opacity levels, power levels, and optical levels set to match real glass. From there, we took our parameters and applied them to a sphere to get a quick approximation of what our base material would look like before it was applied to our model. Once the material parameters were set up, it was applied to the lens that Tanner designed. From here, we can see a barn door light source, so just a rectangular prism of light coming towards the lens. And as it enters the lens, it is being reflected into parallel lines to be collected at the back. As you can see in the back bottom image, the light, even though it's incoming at an angle and it splits off from what appears to be the light source at the floor, it's all one straight line and is parallel with itself, allowing it to be easily collected and transmitted down the fiber optic cables. From here on out, I'll be giving it to Brian, who will be talking about our other simulations.
Okay, this is our stress simulation. Since we know the model will be in an extraterrestrial environment, we know that it will be significantly impacted. It is important to conduct the simulations on these of these environments to visualize how our model is impacted and see what materials could be used to improve it. This is our model in sim scale. The program creates nodes that are applied with stresses, which are then inputted to a matrix, to matrices to see what forces could cause our model to fail. Here is our heat sim. For the heat aspect of our model, we did an overall sim. We mostly focused on the parabolic reflector and the Fresnel lens. Since light also gives off heat, we were able to use the heat simulation results to give another guide on how the light in a lunar environment would be gathered and refracted. In the figures we see, light is gathered and reflected by the parabolic reflector towards the Fresnel lens, where the light is gathered and shot in a single direction for transference. I'll now pass it to Anselmo.
So overall, as a small summary, our simulations were the biggest factor in this in making this model, as they gave us all the data, told us we were on the right path or not. We believe we did achieve a model which satisfied the requirements. Each individual part, had its own purpose, and it was efficient in the model overall. In conclusion, our beginning goal was to achieve a compact, portable, and minimal parts device used for gathering solar energy in a extraterrestrial environment. We believe this model has achieved the entry points, and in the future we plan on developing a hands-on model for further development and do in real-world and extraterrestrial environment testing.
All right. Thank you, guys. Again, thank you to everyone for tuning in and listening to our presentation. Real quick, I want to give a special thanks to Houston Green and Christopher Mendel of Jacobs Technology Incorporated. And the floor is now open to questions and comments. Thank you.